4 elements in the array. We want to find the minimum number of comparisons to sort this short array. Okay, yeah. All right. Because this question is related to the insertion sort. So I put it here using the, similar insertion idea, but we need to do some modification. Okay, all right. Yeah. So when we start, can we try insertion sort first? Yes. Yeah, first, let us try the insertion sort. On the array with 4 elements, x1, x2, x3, x4, and see how many comparisons we need to use for the worst case. Yeah. Here, we look at the worst case. Not the best case. Yeah. Why worst case, not the best case? Because if you can solve the worst case, you solve the whole problem. If you just solve the best case, you have many other cases you have not solved them, right? Yeah. So that's the reason, in order to solve this problem completely, we need to solve the worst case. All right, yeah. Insertion, yeah. So for insertion, when you have x1, you start from x1 and you insert x2 into this one, you need 1 comparison, right? Yeah, 1 comparison, this step. After that, you have x1, x2 sorted, but you need to insert x3 into the sorted array. For the worst case, how many more comparisons do you need? You compare x3 with x2 and then with x1, so you need 2 comparisons. Okay, all right. After that, you have x1, x2, x3 sorted, but your last element x4, you need to make it join with the first 3 elements and find its right position for the worst case. How many comparisons do you need for the worst case? Okay, you need to compare it with x3, x2, and x1. So for the worst case, you need 3 more comparisons. After that, you get a whole array sorted. So now you add up these 3 steps, 1, 2, 3, you get 6 comparisons. Okay, yeah. That means you have a 6 comparison solution for this question. 6. We don't know if this is the best. We don't know. Best or not. We don't know, but we just know we can use 6 comparisons to solve this problem. Next question, can we do better? Yes. Is it possible to use 5 comparisons? That's the question, right? Is it possible to use 5 comparisons to sort the whole array? Right? If you can, then we should take that 5 comparison solution, not the 6 comparison solution, right? Yes, let's try. Can we reduce just the 1 comparison? How about that? Reduce the comparison number just by 1. Yeah, let's look at the last step. All right. In the last step, let's look at our work here. X1, X2, X3. Now we want to make X4 find some appropriate location in this array. It's a sorted array. We know it is sorted array. We can take advantage of this property. The data is ordered. Okay, data is ordered. In order to find the right position as fast as possible, we do not need to compare in order. X3, X2, X1 order. Can we jump faster? Right? Yeah. Some of you, if you connect to the binary search, when we do binary search, we compare X4 with the element in the middle. Okay? Then there are 2 possibilities. Either X4 greater than X2 or X4 less than X2. X4 less than X2. Okay? If X4 greater than X2, then we just need to do 1 more comparison with X3. If X4 less than X, we just need to do 1 more comparison with X1. That's the binary search idea. If we apply the binary search idea, you can see for the worst case, we just need 2 comparisons. For the worst case, we do not need 3 comparisons. We only need 4 comparisons. That's better. Yeah. So then if we modify our last insertion operation, we can improve our total number of comparison 1 plus 2 plus 2 equals 5. You can see this time we find a 5 comparison solution. We find a 5 comparison solution. 1 fewer than the standard insertion. How about that? How about this solution? Okay. Yes. All right. Yeah. Then, after we get this 5 comparison solution, another question. Can we do better than this 5 comparison solution? Can anyone use 4 comparison to sort a given array with 4 elements? Yeah, right? Yeah, because you do not know if you can improve it or not, right? Yeah. How do you know you get the best solution? Right? 5 is the best. Do you know 5 is the best? Best or not? Yeah. So that question also very interesting. Yeah. Because you cannot go forever. You have to stop somewhere, right? You cannot, you know, improve from 5 to 4, from 4 to 3, from 3 to, you cannot. At some point, you have to stop somewhere, okay? The question is, which step you have to stop? At what place you have to stop? Think about that. That question, pretty hard, okay? Pretty hard, yeah. Do we need to stop after we get 5 comparisons? Or after we get 4 comparisons. Okay, yeah, all right, yeah. So here, the answer is the best solution is 5 comparisons. Okay, we already get the best solution, not 4 comparisons. Nobody can use 4 comparisons to sort a 4-element array for the worst case. Okay, yeah. Do not tell me the best case. Yeah, best case you can do faster. Yeah. Best case you can use 3 comparisons. Yeah, but not the best case. The worst case. The worst case, nobody can use 4 comparisons to sort 4-element array. Yeah. But the question is, how do you know you cannot, right? Here, I just tell you the answer, but the question is, how do you get the answer? How do you know this is the answer? That question is important, right? Yeah. We need to know that question. Okay, yeah. So here I can tell you the method to find that answer. Tell you the method to find that answer. Yeah. The method is this. The method is this. Okay. All right. We have n elements. So the given array, there are n element array. Yeah. Here our n equals 4. Okay, all right. All right. Okay, yeah. Then the lower bound. So there is a lower bound we can calculate. That is the minimum number of comparisons you need to sort the array. You cannot break that line. That line is the very bottom. You hit the bottom. You cannot pass that line. So we have that formula. Okay, so that is log base 2 of n factorial ceiling function. This is the, very bottom formula. All right, yeah. Here, n, so let's look at when n equals 4, we need to calculate ceiling function of log base 2 of 4 factorial. What's that number? Okay, yeah. Log base 2, 4 factorial, 4 times 3 times 2 times 1, 24, right? Ceiling function, okay? Ceiling function 24 is greater than 16, but less than 32, right? That means log base 2, it should be 4 point something. 4 point something, you take the ceiling function, you get a 5. 5, this number, 5 is the very bottom. You cannot do better than this number 5. If you reach 5, that's the best you can get. You cannot get 1 fewer than this lower bound number, 5. So 4 is impossible. Okay, yeah. All right, but the question is, some of you may think about, how do you know that formula, right? How do you know that formula? Log base 2 of n factorial seeding function. How do you know that, right? Yeah. Actually, we can prove it. We can derive it. We can derive that formula by a special technique called a decision tree. Decision tree technique. All right. If I can find some time, I will show you that decision tree technique so we can find the slow amount formula. Then when you do the checking, you will know where to stop. You cannot go forever, right? You cannot reduce the comparison number one at a time forever. You have to stop somewhere. This is the place you have to stop. Okay? Yeah, not forever. That's the, very end for the solution. Yeah. All right, so that's it. Yeah. Let us stop today's lecture right here and try to work on the homework assignment number 1. There are some challenging questions. So if you have questions, you can ask me. Yeah. Homework number 1. So I give you about 2 weeks to complete it, but still don't waste your time. Yeah. All right, so that's it.